bracket or platform for a security camera to enable it to pan, so like left and right, or tilt, so in that direction, in 2 different axes, using 2 electric motors. And this would be to improve the security camera footage at lower cost, for example in retail, like shops or any indoor kind of application. So you can use a single static camera that can pan left and pan right.
So instead of having multiple, you just have one.
Having multiple cameras, or you can upgrade. If you have a camera point, you don't have to pull more cabling in and add cameras. You can just mount your already installed camera onto this platform and make it pan tilt. There are newer cameras that have a motorized zoom in it, which are a whole lot cheaper than a camera that has pan and tilt and zoom already built into it. So you can integrate that zooming camera with my design, and then you can use the zoom of the camera and autofocus of the camera, and then the pan and tilt is done by the platform. But that's only if you want to put in a new system. In the background sort of research, I had a look. There are pan and tilt designs, but they're for photography, and they're like quite bulky, and I wanted to sort of try and make mine as compact as possible. As I said, built-in pan and tilt CCTV cameras are quite costly, starting at like about 4,000, whereas a normal camera I showed there is about starting at like 500. Yeah, and then I sketched some designs that I sort of looked at on the internet for a bit of inspiration, and then what I did was I thought of an internal gear, so at the bottom like a planetary gear like that, and then driven from the internal with gears around the outside. Or then I thought of a platform like a hanging camera base with two opposing with motor inside, so that like if it's a platform above, platform like that, and then a U shape like that. So that was a different design I thought of. This is Richard showing me that I need 2 bearings to keep stabilization. Otherwise, if you use 1 bearing, then you'll have play in it. And that's more what I decided upon that one. So like I have a hanging platform because it's more compact than that height there, I think, if you add a camera on top there as opposed to putting a camera inside there. That was the final design that I ended up with. The bevel gears I decided on because I could like turn this motor 90 degrees to try and keep it least protruding, so compact and least overhang, and also upside down motor there with a gear driving that gear there. So that's the motor, just a simplified model of the motor. Also for compactness, to keep it small in that direction there. Yeah. There's a photo of the final design. What I used was Perspex and for the platform there. Also Perspex for these bottom gears. That's 6mm Perspex, and I think 5mm here, or 4. And there's the 2 DC motors, 12-volt DC motors. They are 24 RPM for this one, and then 100 RPM for this one. So that was what I had to decide on eventually. After I tried hard drive motors, we found it was like difficult to control their speed, and they weren't suitable for the amount of torque needed to turn this platform. And obviously the speed is much too high. We tried with different controlling circuits and motors from drone equipment and stuff.
And stepper motors?
I tried to stay compact as possible, because I started off with like a drone motor which is like 25mm diameter, and stepper motors I tried to be a bit more like simplified in cost and stuff. I mean, I know stepper motors you can get for cheap, but I was just thinking a basic I think where you could just do a basic switch circuit with variable voltage if you wanted to. But these work at
Instead of an Arduino, instead of a microcontroller.
instead of having microcontrollers and stuff, which would add to the cost. So just with normal switching, you can stay at 12 volt, which these motors are spec'd at, and the speed is suitable. I mean, you could go from like 5 volt up to 12 volt to slow the speed and higher the speed, but your controlling would be more expensive then. Other stuff I used was 2 bearings there in the bottom, in the center there to fan like that. M3 and M2 bolts and nuts to hold the components together, and 6mm rod and 2 bearings for that, so a piece of rod there and then a rod there. 3D printing is all the grey parts and the black part there for the 2 bevel gears and the white there, and also those 2 side brackets. Problems I found was with Perspex, the number of teeth on the Perspex gears. I started with I think around 140 teeth on that, and always on Solidworks you zoom in and you're looking very closely at your design, and you always think it looks big enough, but then you measure it and you find it's 1 or 2 mil, and then you kind of think in real life 1 or 2 mil is not going to, it's a bit fine. So then I changed it to 75 teeth, so half the amount of teeth here, and that gave it more smooth and just less iffy off the top, so it was more tolerable to slight movement. If this gear wasn't centered properly, because if this gear wasn't perfectly centered, then it would push or be too far away from the driving gear. And also the imperfections of the laser cutter, and it would blow like bubbles if I cut. That was firstly 8mm, and then I changed to 6mm here, so it cut through 6mm a bit easier, and then the bubbles and stuff was less of an issue on coarser teeth.
Because that's cut a bit faster.
Yeah,
you need a bit of speed.
I think I had to cut that twice through on a same speed, yeah, to make sure it's cut through. Right, and then including in that problem, then it later caused, because I'd already printed the stuff, and then I changed this gear there is a slight bit smaller in diameter to that gear, so I had to add a bit of clearance in this housing of the gear. So with the Dremel tool, just clearance, yeah. And again, clearance on Solidworks again looks like it's clear, but then you measure it and you check it's only like half a mil, and in real life, half a mil with 3D printing doesn't really turn out to be half a mil. 3D printing might be slightly bigger. Usually what we find, because if you model a hole for, say, these bolts and nuts, like there's a bolt going up there to mount the motor, you model it at 3mm, then you're going to have to draw it out at 3mm, so rather than model it like 3.4, the 3D printer will be like closer to 3 in the end print. And 3D printing orientation, the last minute I had to split this hanger part into 3 parts, because if you were to print like in layers like this, then you would print layers, small layers up there, and that would be very weak if you had layers like going up in that direction, as opposed to laying that pillar, both of these pillars, laying them flat on the printer and then printing them up in that direction is a lot stronger. So I had to bolt them together. Yeah, I should have put it's called a rib in there a bit more to provide stability. But yeah, 5mm flange over there and 5mm seemed to be okay, I think. But a rib would have helped, yeah. And also placement of the 3D part on the printer bed, when checking that you assume it's 200mm, but there it went off the bed a little bit, so it wasn't critical for the strength, but aesthetically it looks a bit weird. I've spent a lot of time in Solidworks, and I enjoyed learning how to not fight with the thing and actually have a look why the component isn't moving, or and you basically look at relations and use relations to your advantage so that things don't go and move themselves when you didn't want to move them. And with that is
that takes patience.
Fully defining a sketch. With that I say fully defining, so make it black so that so that your print, or when you change components or move components, then you reference to say that line, that distance, or where am I, like that distance we referenced there, but then change this guy, move that guy higher, then this guy's also going to follow it, and you didn't intend to do that. So if it's fully defined, then your reference is like zero, it's not going to move. So if you move something else that is not fully defined, it's not going to have a chain effect on moving other stuff you didn't want to move.
Well, that's an important consideration, yeah.
Yeah, so use define
smart dimension.
and also smart dimensions. That is obviously to fully define it. Yeah, smart dimensioning is the main tool, and assemble the complete. So like I did assemble. That's a rendering of the full assembly, so that you can check for clearance. So this motor I found wasn't clearing over here, so I lifted it a bit higher and pushed it out a little bit. At the moment, it's got about a 270 degree, 250 degree rotating ability, because I intended for it to rotate up to that pillar and up to that pillar. But in actual fact, when I finished printing, even assembling it on Solidworks, you overlook that this corner slightly touches the motor, but mostly that would be controlled. I would put a limit switch, start and stop, so that you surely have your motor not touching any equipment when you're panning and tilting it. Limit switch just to cut the power so that you won't run into problems. Then that was, yeah, a lot of time spent on SolidWorks. I enjoyed doing the tutorial projects. So that's a quick GIF of the movement of the mini 12-volt compressor that we drew as a tutorial project. And yeah, a lot of the practice here helped me to know how to draw this whole design. Yeah. Time management, I think I worked quite well with time. I always thought that spending quite a long time designing on SolidWorks before printing, and yeah, I mean, try and plan rather to have your dimensions correct from the start, because that distance there was coincident there, so that I added there to make this platform a little bit bigger, or to accommodate later. I was looking at other cameras, like, is this thing really big enough for larger CCTV cameras? So I made it a bit bigger, and I also think that assisted with your center of gravity if you add more weight, because that's quite a lot of weight there. If you push the camera you're going to put on top of the platform, if you move it a bit more across to the right hand side, you then have the center of gravity above that bearing over there, those two bearings. So, but with that, then obviously the full rotation won't happen, but we can't do that in any case because of the sort of wiring that. I knew it was going to be a problem, the wiring running this motor, but using this flexible sheath to guide the wiring, so you would have a loop going from the top to fix the wiring, so that you have a bit of a hanging arm of wiring, so that the wiring doesn't tangle itself up, but you're only going to pan 270 degrees at most. Electrically, I could have carried on a bit more, but I focused mainly on the mechanical stuff, and I
did
enjoy it.
From this turn.
Oh, I've got a video on there of the turning, but I can show you. It's
Sure.
not
Yeah,
right.
it is.